Thank you everyone for dialing in this evening. I am Suddhasata Saha, a pre-final year student of Mechanical Engineering from the National Institute of Technology, Durgapur. And today I would like to talk to you about rovers and extraterrestrial robotics. So I hope I can start. I hope you can hear me, guys. I just want to make sure that you can hear me. Fantastic. So,
Yes.
okay, let me share my slides with you. So once I start the PPT, just let me know if you can see the PPT. Okay.
Okay.
So can you guys see the PPT?
Yes,
Yes.
Okay. So today our topic of discussion is about rovers and extraterrestrial robotics, as I already mentioned before. And without further ado, I would like to start this wonderful webinar. And thanks to the STAC team for giving me this opportunity to present before you this interesting topic. So before I begin, let me tell you after this webinar, what are the things which you will get to know and learn. So first, you will get a good introduction to rovers and extraterrestrial robotics. And then we are going to have a brief overview of the various subsystems which are in action. And then we dive into the beautiful world of mobility systems which help the rover to move or rover surface. And I will provide some sort of design insights as well, as much as possible in this 1 hour window. And then we will explore the various rover innovations and the challenges and how they are solved by these esteemed organizations like ISRO and NASA. And then finally, I would like to address this thing, which is how you can perhaps build your own rover, which is fully functional and will be a nice little piece of robotics to work with and learn a lot of stuff. So let us begin the first part about so what really is a rover. So to put it straight and simply, it is basically an unmanned vehicle which is used for planetary exploration. You send something to the planet you want to explore. So why only rovers? Because you see, if you send human beings to other planets or other celestial bodies to study, these manned missions are very expensive. So we need to do some cost cutting and make it as much economic as possible. So maintaining that type of framework in mind, we build robots which are capable of going to another planet and taking autonomous decisions, conducting scientific experiments on board, thinking about these decision making processes, and then they analyze soil samples, rocks, etc. They gather data, they collect imaging using their high resolution cameras, and various types of sensors are there to detect weather and environmental changes and all. And so rovers are these objects which are, you can say, an epitome of space exploration. And they also can be used in human rescue operations. Like, you can send them to places where humans cannot. We can achieve that type of resilience and durability and robustness in that type of a design of robot, which can basically perhaps defuse a bomb. So okay, with that I would like to proceed. So what are the applications of a rover? Some basic applications, like as I already mentioned, planetary exploration is something which forms the crux of making a rover.
hello.
And yeah,
Can we get the PPT after the presentation in group?
yes, I will make sure everyone gets this PPT.
Okay, okay. Thank you, thank you.
Yes, 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 definitely. So then after this, another application which is specifically important for any sort of exploration mission is conducting scientific investigations, or you can say scientific research. Basically, when you go to another planet, you need to analyze the soil samples, the weather conditions, and also the type of rocks which are there, whether you can analyze the elemental composition and you can derive something from that. So these sort of investigations require the possession of very good scientific instruments, and hence rovers are a medium of conducting scientific experiments on other planets where the humans might find it difficult to do the same thing. And then we can also, as I already mentioned, that we can use them in search and rescue operations on earth itself. So we can build rovers which are very tough, and they can go to a place and they can diffuse bombs. So we can have some bomb diffusing modules on our rovers. We can also potentially use them, something I've not mentioned here in the slides, you can use them in defense applications. Kind of rovers actually have better mobility than ordinary tanks, so we can use them in place of tanks and build some sort of futuristic vehicles perhaps to fight with our enemies. And also one of the major aspects of rovers in scientific applications is about monitoring the environment, because climate change is a big issue, and rovers have all the apparatus you need to conduct tests and monitor and analyze how weather conditions are changing, and what environment is basically there in the space outside. So in whichever planet you go, they will kind of measure wind speed, then they will detect the regions of illumination by sunlight. So these are the things which they do, and they collect data and analyze how much erosion has taken place on the planetary surface and all that, to get some conclusions. And that form the basis of our studies about the environment also. So then, so why do we need rovers? Basically, as to put in, it is because you see these space missions, about in particular missions where you need to put something in the outer space, and long distance communications are coupled with these unpredictable conditions, right? So we need rovers because you see these environments are extreme, like there are extreme temperatures, radiation exposure, and the gravity matrix is also different for different planets. So we need something which can be capable of exploring different terrains, unpredictable terrains, and very diverse areas of exploration. And then we have this beautiful point of cost effective exploration, because it is very much cost effective to send something which is unmanned, basically, which is capable of doing stuff without human intervention in real time. And then we also need rovers as they serve as a medium of scientific discovery, as already achieved by our previous rovers which are deployed in the Mars and Moon by the various organizations. I'll come to that later. And also for preparation for human missions, like the scientists need to do certain amount of homework before sending astronauts, or you say humans, to another planet. So they need to get some complete understanding of that planet, the conditions there, or any celestial body for that matter. So rovers can be used to do that homework for them. So now we jump into this domain of extraterrestrial robotics. So yep, it is a new jargon which is very big, but if we break it down to small parts, so there are two terms: extraterrestrial and robotics. Extraterrestrial is basically anything which is associated with something originating or existing outside Earth in space conditions, so, or operating in space conditions. So basically extraterrestrial robotics indicates the design, development, and deploying these rovers or robots in space, where it is basically outside Earth and the atmosphere of the Earth. So in simple words, we can say that this is space robotics. So this is a technical term, but it is much more, there is much more to this than just this big jargon. So now I will touch upon some few key elements of extraterrestrial robotics, like the autonomy, by which I mean that you see in these rover operations, there is no real-time human intervention. So which means the rovers, when once the mission starts and their mission period ticks in, the rovers really need to take on-board decisions about what they want to do, which path they need to traverse. So they need to design an optimal path on board. Sometimes when there are communication delays, and as you already know that the planets we explore are far far away from our Earth, by very large magnitudes of order, and therefore there should be some degree of autonomy in whatever the rover does in another planet or another celestial body for that matter. And so by autonomy I exactly mean the ability or the degree of freedom the rover has to take independent decisions itself and to perform tasks like, to collect soil samples, to when to understand, to sense something. So it has to take a set of decisions, a very well defined set of decisions, basically whatever we do when we are put in a situation, in a set of circumstances. So the rovers must be able to do that, because it is not possible always to remotely control them from Earth or any spacecraft nearby or any orbiter for that matter. So we need something that makes them much more autonomous in their operational nature. Now we come to the important aspect and another key element of this extraterrestrial robotics, which is durability and resilience. You see, as I mentioned previously, these rovers are subjected to extremely harsh conditions, which I exactly mean that they are subjected to unpredictable terrains, right? Rocks, and there are craters, and there are little mountains, big mountains, dunes, and nobody knows what exactly is there on planets which are unexplored yet. So you have very diverse set of conditions, and then you're subjected to radiation, and then to these dust, lunar dust say, or Martian storms, etc. So these are certain things which might erode and cause wear out of the rover and its sophisticated instruments. So something in designing rovers which I will mention again is that when engineers of NASA and ISRO design rovers, they try to make it as much durable and resilient as possible. Like, that is, they try to increase the lifespan of a rover so that they can operate for longer periods without requiring any sort of maintenance, and without, like, they kind of try to make it self sustainable so they can sustain themselves, and in a sense also self sufficient as well. So I would like to say that durability and sustainability and resilience in case of rovers is something extremely important, and it concerns with the material selections as well, because the type of materials particular guy will choose for making a rover more durable will actually have a long term impact on the overall mission, because these missions are not cheap. These are extremely expensive missions of the order of $2 billion or so, so as to say. So they cannot just take any sort of operational risk. So they have to build things which are extremely durable and resilient to any sort of condition ahead. And so self repairing mechanisms must also be in action, so that in case of emergency we have plan B. Then we come to this important part of scientific capabilities, which defines a rover's operational success. So you see, scientific capabilities, by which I mean that these rovers are equipped with various tools and scientific instruments to collect soil samples, to analyze rocks, to collect, you can say, specific samples which we want them to collect by using, say, a robotic arm which is there on board the rover. And using this various samples collected, it will also click pictures. There are imaging apparatus, there are high resolution cameras provided. Okay, so they will also click a lot of pictures of that surface, and these data will be sent back to the Earth. And in fact, interesting enough, the rover also performs a lot of experiments related to bioscience on board real time during their mission, which means that the rover is actually capable, if I connect it to that autonomy aspect, to perform experiments on board while collecting soil samples. They can do some sort of drilling operations, they can do some all sorts of cool stuff, and come up with new data, new investigation, new patterns, and it becomes very interesting in this regard. Then I come to this aspect of mobility, which basically means deploying some sort of mechanism so that the rover can move. So by that I mean, we engineers basically try to design such durable and sustainable mechanisms which are best suited and optimal for these harsh conditions. So I will discuss mobility aspect particularly in this webinar today in a little bit of detail. So I would not like to give any more spoilers about that topic, because it is very interesting to design mobility systems for rovers, because they are very different from what you have seen in ordinary cars or vehicles, or even in supercars for that matter. So rovers have a altogether different mobility system in action. And then we have this aspect of communication systems. You see, these rovers are deployed on uh, planets, and so it is very difficult to communicate with them. So the rovers need, or they are equipped with a set of antennas and transmitters, and sometimes even relay systems to communicate and receive commands from the control center in Earth, or send back data of the experiments they conduct back to Earth. So they need very robust communication systems, because once you lose connection with your rover, it basically means it's checkmate for your mission. So you just lose control. It happened in the Chandrayaan mission that after some time the mission died. So this happens, and it is the failure of the communication systems is something which is already predicted and calculated, and it is very well incorporated into the mission that by this duration this thing might fail, or this might work. So as per that, the communication systems are developed, and it forms a very important part of kind of keeping all the elements together and sending data back to across such large distances in space, in the vast space. And then we have this very important and central topic of discussion, that is power supply. Power supply is the very central topic of discussion, because you see, without any sort of good and sustainable power supply, long lasting power supply, it is very difficult to continue these missions, because the rovers consume a lot of power. And in the sense, I say that they are this whole affair of building a rover is involving multidisciplinary research. Like, somebody is involved in doing bioscience research, somebody is building up these machines, somebody is building up these communication systems, and somebody is writing some algorithms for the rover to do autonomous navigation. So then there is this artificial intelligence into action. There is various sorts of learning modules for the rover, image processing, and all sorts of different things come up, and even aspects of scientific importance as well. So power supply needs to be something which is very much robust. And for an example, like, certain rovers use solar powered sources, certain rovers use nuclear powered sources, and I will mention them later and how exactly they happen. So power supply is something we need to put thought into, because we need to design something which is very much sustainable, and it is very much foolproof, because if the power system fails, then basically it's off and dead. So it is what keeps the rover alive, as to say. And so next I move on to the various subsystems of a rover. Now we are looking into the rover as a robotic object of interest, and we will break it down into small domains of research and how they are actually built like. So fundamentally, rovers can be classified into three broad domains. It would be a mistake to compartmentalize these type of fields of engineering and science, because ultimately at the end everything is connected up, and everything is the part of the same fabric of this universe. So anyway, without diverging much, so one of the main components, or fields in this rover construction, is the mechanical domain. This mechanical subsystem is has other names as well. Like sometimes it is also referred to as mechatronics subsystem. So basically electromechanical subsystems. So by which I mean this subsystem particularly is devoted for the design, development and research of the robotic arm which is there on a rover, the suspension system for the mobility system, the bioassembly, which is the the set of apparatus for conducting bioscience experiments for the rover, the chassis of the rover, and the mobility system itself again. And also the mechanical domain deals a fairly good amount of design analysis as well, by which I mean that before making this type of a rover, a lot of math goes into the behind the scenes. Like a lot of simulations are done in game environments, and we study what are the impacts of this design, which design is better, which design would be optimal, and all those factors are considered before finally picking a particular design. And then a lot of mathematics also goes into, as to say, there's a beautiful subject called vehicle dynamics which is in action before deciding that what type of mobility or suspension system is to be designed for being able to face such unpredictable terrains which are very bumpy and hard to maneuver them. Now we come to the other topic of the other domain, which is electronics and computing. So basically, I have merged two very different domains together to fit this whole system into a 1 hour webinar. But okay, it won't cause much problem. So the electronics and computing subsystem basically deals with two aspects: the decision making algorithm and intelligent system subsystem, which means that the rover has a sort of electronics into action, and the rover also has a sort of algorithms and a artificial intelligence model which is taking decisions on its behalf in real time without any human intervention. So by that I mean that this electronics and computing subsystem has the various control algorithms, computing unit, sensors and actuators, navigation modules, communication systems, and this power management aspect is also covered in this subsystem. So which means that the rover has a single board computer on board, which is like the host PC for it, and it takes decisions on its behalf. And then we have this computing unit, some control algorithms which are building up this uh, learning environments for the rover. And we also need a very robust foolproof navigation module for the rover to autonomously navigate the uncharted terrains of any sort of celestial object planet. So which means that these rovers are an epitome of self-driving research. So the best of the best self-driving modules are employed in rovers, so that the rovers can be easily deployed in any sort of unpredictable terrain, and maneuverability is considered a challenge in this aspect, because long distance communication is very difficult. So we need very good communication systems in action as well. And now finally we come to the another aspect which deals with the scientific investigations which are conducted by the rover, the scientific experiments which are conducted. So it is the bioscience domain, the subsystem. So the bioscience subsystem also deploys engineers from both the electronics and computing domain and the mechanical domain, because we need to build hardware and software for the rover to conduct experiments related to detection of life, which is very interesting, extraterrestrial life, potential for having water or stuff. So basically life detection test, biosensors are there, geological surveys conducted, sample collection, and all those beautiful imaging systems, they also are developed by this bioscience domain. And then there comes this aspect of data processing and storage, which is again coupled with this domain of the computing unit of electronics and computing, because after processing you need to compute a lot of data and you need to take out conclusions. So extraction of data and then analyzing data in real time without any sort of remote or command operations. So that is something which makes the rover operations very different from that of any other object of mechanics. So then we move into the particular element of focus of extraterrestrial robotics today, which is rover mobility systems. So I have given a very brief intro into these various subsystems. Like we can go at depth and discuss for hours about each of the topics, but so I have to keep things in this time frame. So I would like to discuss something which is apparently very interesting and at the same time challenging to construct and analyze, which is this mobility systems. So they basically mean something which you deploy, which makes the rover move. In case of cars, you have a suspension system, you have an all-wheel drive base. So basically that is how the car moves. So but in the case of rovers, you see, it is subjected to a very diverse terrain, which means that depending on the mission, like if you want to explore the surface of a planet, you can employ an all-wheel drive base similar to a car, but not exactly. A beautiful suspension system to absorb these shocks, and you have seen those monster trucks in movies, so you can do that type of construction. But that requires a great deal of study and analysis of vehicle dynamics to put this into action. And it is very beautiful. Like it is like putting all those jigsaw puzzles together and creating the complete picture. And when you look at it, then you feel the beauty of this beast. Then we have this other option for going through these uncharted terrains. Like you can employ something which is inspired from how caterpillars move. So caterpillar tracks or conveyor belt mobility systems. So basically a belt which is moving over to moving discs, and it is deployed in tanks, because tanks also they explore surfaces which are very much similar to rover like surfaces. So a caterpillar tank can be deployed as a mobility system for them to rove. But then there are various degrees of failures which various subsystems have been subjected to, and only the best mobility system has been selected so far and is in action. But new mobility systems are also being developed. Like if we inspire directly from nature, like there are for these low gravity environments, there are these hopping and aerial systems. Like if you just employ a drone instead of having wheels, so that gives us a new dimension to exploring a surface using a drone. So also there are these movements of a spider which you might have observed. They are very precise, fast, quick, and flexible. So we can have something of a sort of a legged mechanism, which is very powerful way actually to climb hills and go down craters, and which is something the wheels find very difficult to, because they endure a lot of wear and tear due to the extreme conditions. So the particular mechanism which was selected for the rocker is called the rocker bogie suspension system. This is a very interesting and a new kind of suspension system which is already deployed in all rovers which the organizations have built so far. And I have provided this animation so that you can understand what exactly is this rocker bogie, because I can talk a lot, and but that might not make sense, because you need to actually visualize stuff and kind of put things together to understand the complete picture. You see here there are two different links. This is one link and this is another link, and they are having some sort of revolute joints, so they can turn. And you can see there are total 6 wheels, 3 on this side and 3 on the other side of the rover. So this type of an arrangement, as you can see, is quite easily climbing obstacles. And the most interesting aspect of the rocker bogie system is that it is made in such a way that all the 6 wheels maintain contact with the surface of the planet at all times, irrespective of the nature of that surface. And this is, you might ask that why would we need that type of a objective to achieve. This is because for rovers, they are charting this type of hilly and sudden depressions are coming in this surface, so they need to have a high degree of traction. And the only condition which satisfies that these rovers will have a lot of traction is that you need to keep all the wheels on the ground at all times. So that is something achieved very easily through this rocker bogie suspension with a few improvisations as well. This is a very simple schematic representation. The actual rovers have more robust and more complicated rocker bogie, but fundamentally it boils down to this, system which you are seeing now. And to give you, yes,
Why don't we deploy drones instead of rover?
I will address your question at the end of this webinar, and it is a very interesting question. So you might jot down your questions in one place, and then you can ask me. So I'll answer all your questions. Is it
Okay, okay.
okay? Yes, yes.
Yes, yes, yes.
Thank you for cooperating. So you see this. Suspension system to for the actually conquer an obstacle which is about half the rover can climb up obstacles which are twice the size of its wheels. So you can get an quantitative idea of exactly why we use this type of works. Now I would like to discuss another important element in very brief, like the rocker bogie you saw. So the rocker bogie is coupled with a differential pivot, and in simple terms I would like to explain you that what exactly is this differential pivot. You see, this is the rocker bogie, and there is similar structure assembly on the other side of the rover. So these two are connected with a sort of a rod, and it acts as a differential. And first let me play this video so you will get some sort of understanding. You see, the basic function of this differential pivot is that suppose this rover encounters an obstacle in its path, right? This one. So what this is doing is the differential pivot transfers all the weight which is on this side to the other side, say from left to right or from right to left. So which means the differential pivot is basically transferring the weight of the obstacle to the side which already has a good traction. So that ensures a more stable locomotion of the rover, and that makes both the rocker bogie sides to move in sync. Otherwise this would face a lot of difficulties, and it would probably kind of topple. So to prevent toppling of the rover, and to prevent loss in traction, this differential bar is transferring the weight from the side which is facing the obstacles to the other side. So that makes the rover a lot more stable. And here I have not mentioned a certain thing, which is I would like to draw a very gross analogy, which is you might have seen those skyscrapers. So in those skyscrapers, when earthquake takes place, there is a sort of heavy ball which is suspended inside that skyscraper, which oscillates and maintains uh, the balance of the structure. So that type of a mechanism which prevents that tall structure from toppling is also involved in shifting weights or transferring weights to the side which is more stable. So it is an analogy, but you can understand it that way, that it is helping it to remain stable no matter what the either side of the rocker bogie encounters. And so that helps in kind of going over any sort of obstacle. That is how things are. And now I would like to come to this aspect called rover innovations, the various challenges which are faced by these esteemed organizations like ISRO and NASA and the European Space Agency and all those. So first I would like to start with ISRO's Pragyan. I hope you all are aware of Pragyan, which was the rover which was deployed by ISRO on the surface of the moon in the South Pole, and they got a tremendous victory by being the first nation to to achieve such a massive feat of deploying this rover in the south pole of the moon. So we as Indians should be extremely proud of this achievement. It demarks our technological superiority in these space missions, which was something, the vision of our great revolutionary father of Indian space science, Dr. Vikram Sarabhai. So if he was alive today, he would be very happy about this progress we have made. So Pragyan of ISRO, you can see an image. I have used a very detailed schematic. I have not used the actual image so as to, because help you understand what are the parts of this rover, an actual rover. See, you are seeing some sort of skeleton structures all this while. So now you are going to see some actual rovers, which are engineered by organizations like ISRO and NASA. So here you see, this is the platform which has all that, it houses all that scientific instruments and robotic arm and all. Pragyan did not have a robotic arm, but it has a load of scientific instruments and apparatus to conduct experiments, and real-time data analysis mechanisms are there. And then you can see there's this electronic box, and this is the rocker bogie which I just showed you. So the same rocker bogie is used in Pragyan as well. And then there are two navigation cameras, you can see, which are capturing the field of view and then processing that data through image processing by doing computer vision and all sort of stuff to navigate the terrains. And this is the chassis, and so the rover is powered by solar energy. So you can see a very nice structure of a solar panel. These are the receiving and transmitting antennas, and this is the solar panel. So it is designed in such a way that it can be folded to the other side. It's like opening a pencil box. You see, it opens up like this, pops up, and so the sunlight is incident and it is captured by this solar panel, and that powers our rover. And this is the differential, you can see midway, which is connecting these two sides of the rocker bogie. And this is the wheel assembly with the bearing and load bearing threads and all those. These are the threads on the wheels which are responsible for the load bearing functions. So now what are the the merits of this Pragyan, like that, the features of this? It is basically solar powered, something which is used in space operations of this type. So, and that makes it a sustainable energy supply also. So Pragyan is also having autonomous navigation for exploring the uncharted terrains using a navigation module which is having a lot of autonomy in it, decision making. So it can make its own decisions as to which path is optimal and which way should the rover traverse, and so that it can minimize obstacles on its path. Then we have these boatload of scientific payloads, like payloads, by which I mean that the instruments which are there, which are carried by this housing case. So in particular, I would like to mention two of the payloads, which is in Pragyan of ISRO, which is the laser induced breakdown spectroscope, LIBS, and an alpha particle X-ray spectrometer. These two are there for analyzing the lunar soil and conducting all sort of experiments. And I would not like to go in much detail about them at this moment, because I have other rovers in line waiting for their turn to come up. So before I finish about Pragyan, I would like to first show you a video, a historic video about how Chandrayaan-3 rover, it first ramped down through that lander vehicle to the lunar surface, and that marked the so you see, this is the solar panel which is there. This is the rocker bogie. This is the body of the rover. So I hope you enjoyed that video. It was a historic video celebrating the success of Indian technological advancement in space science, as foreseen by Dr. Vikram Sarabhai and all the intellectual giants, Satish Dhawan, and then we have others in that. So the challenges of this Pragyan rover in particular was the lunar dust, which means that it will cause wear and tear, and it will also uh, put up a tough fight to the durability and resilience aspects of the rover. Like the lunar dust has this abrasive uh, nature of destroying any sort of apparatus which is deployed on the moon, and this also affects the integrity of the instruments which are there. We also know that, as you are aware, that the moon has a lot of extreme temperature ranges. A wide spectrum of temperatures is what you see. So that could also affect the thermoregulation of the rover. So when engineers design these rovers, they need to deploy a sort of mechanism which can control the thermoregulation, for that matter, like the temperature aspects of the rover, so that circuits do not fry up and things do not go haywire. Like it can be extremely cold, like it can dip down to as much as 1 minus 130 degrees Celsius, and certain the material properties might change of certain things. So that is why thermoregulation of rovers is very important, and that is a challenge every rover faces, and so does Pragyan. Then there are communication delays as expected, because the distance is, it is very large, and that results in sudden delays, and then sometimes the mission goes off, sometimes it switches on again. So these are very difficult aspects to address, and because in real time, if you fail to communicate with the rover, then you will lose leads about the planet you are exploring. So you need to have very robust communication systems. Next, we have next in line we have Curiosity, a rover with a beautiful name, and it is indeed curious because it is inquisitive in exploring the Mars. And we will discuss a very important failure of Curiosity, because we learn from failures. We learn a lot of things. So this is a close-up image of the Curiosity rover. As you can see, these are the intricate details which are put into the wheels, for that matter. These are the thread patterns which have this load bearing aspect. And then there is this rocker bogie system which you can see close up, and this is the body, and this is how it is. It is this big. It is way bigger than Pragyan, and it is very heavy. So Curiosity has a boatload of innovations, and I would like to discuss a few. Like it has a very advanced scientific payload. So it is equipped with a suite of sophisticated instruments and other such stuff for analyzing. I've given it in the PPT. Now, something interesting about Curiosity is that the power source is nuclear. It is the nuclear power source, which is a very reliable and long-lasting power supply. The Curiosity deploys a RTG, which stands for radioisotope, and the T stands for thermo electric, and G stands for the generator, radioisotope thermoelectric generator. So which basically means, if I break it down to simple terms, the power supply uses an array of these thermocouples to convert the heat which is coming out from the decay of any natural radioactive material into electricity. So it is basically converting the heat from a radioactive decay into electricity, and that powers the rover. It is of the order of a few hundred watts or so, but it is very efficient in driving these operations. So where in fact you might say that why not use the solar panels, for that matter, because this nuclear power source seems a very expensive affair, because you see the nuclear power source is having a high maintenance cost and a high one time deployment cost, but it is very much durable and resistant to wear and tear. This is the kind of generator which has no moving part at all. So which means that if it has no moving part, so all those problems associated with objects having moving parts, like the normal generator you see in your home has a lot of moving parts. There's a rotor which is moving, so that causes a lot of wear and tear. So these are very long lasting power sources because they do not have any moving part. So that is something which makes it very special for long lasting operations, this nuclear power source. And then we have this very advanced autonomous navigation module for it to navigate the terrains, and to be able to conquer all those bumpy surfaces ahead of it. Now I don't want you guys to go through all of this stuff. I would like to tell you the story here. So one particular aspect I have taken up about the Curiosity rover is that something we do not sometimes think about is that the wheels of Curiosity, and that was a big problem, and you can say in a sense of failure of the Curiosity rover. You see, the wheels of Curiosity, they were, you can say, half a meter in diameter, and about, it is given, the data is here, 400 millimeter wide. And you would be surprised that the thickness over the circumference is just 0.75 millimeters, which makes it as thick as only a credit card. Because you see, why this type of a dimension is used, because you need the wheels of the rover to be able to carry its weight, the load of all those instruments and the entire rover itself. At the same time, you need wheels which are very lightweight for cost cutting, because the launch operation costs are very expensive. So achieving these two polar opposite tasks at the same time is will invite a lot of damage and will increase the chances of these wheels to, face damage, long term damage, and that will possibly stop all rover operations ahead if the wheels stop working, right? So here comes the interesting problem which came up, and the top priority of the NASA engineers was always to make something which is long lasting. The rovers should be having a high longevity, and so they thought of alternative designs. They did extensive material research, and they wanted something which could, kind of deform and then conform to the terrains of the planet, of the surface they are exploring, because these wheels under that 1 ton vehicle load, they were subject to continuous stress, and they could not retain their original shape. They were deforming, and there was a lot of damage. The load bearing threads which were there, they failed miserably. And Curiosity was known by this problem because the solution was a darn genius. It was the memory wheels of NASA. So you see, NASA came up with a new material research which not only transformed the way we make wheels, but it also transformed material science research as well, because they came up with a material called nitinol, which is a nickel titanium alloy. And the interesting thing is that it has a shape memory, which means you might have heard about fluids, so fluids, when subject to continuous stress, they are zero memory substances. They do not remember their original shape. That is why they are fluids. They have fluidity, they can flow. But materials like nitinol, they have a memory to retain their original shape. And it is through their interesting property of super elasticity which allows these NASA prototype wheels to deform extensively, like from the tire's edge to the axle. This much they can deform and conform to the terrains. And that way they can again come back to their original shape. Thus, that is how they prevent any sort of damage. This is the technological innovation by NASA to address this problem. As you can see here, the damage of the wheels of Curiosity and how they were trying to solve it. But the lunar rovers had some sort of steel mesh wheels, lightweight steel mesh wheels. Like, this is a solid continuous wheel surface, but they had some sort of steel mesh wheels. But this is again a wheel made up of nitinol, and it is not only increasing the lifespan, it is also cost effective, because you all know that I have given a figure here. 2.5 billion is the cost of Mars mission, like Curiosity or Perseverance for that matter. So you cannot afford to make mistakes of any sort, and need certain damage control apparatus to control whatever is getting damaged, or you need some sort of repair mechanisms in action. So these nitinol wheels reduce this mission failure risks, and they have also additionally a very high load bearing capacity. You see, for making the rover wheels to withstand that high load, the surface of the wheels have intricate thread designs. These are load bearing structures which will bear all the load above. But these nitinol wheels, due to their super elasticity and all that, they have very high load bearing capability. So they allow more and more scientific instruments to be loaded onto the rover and push the limits of our scientific innovations forward. Now, I would like to take a look at another rover of NASA, which is Perseverance, made by the Jet Propulsion Laboratory, which is called JPL of the California Institute of Technology. So here you can see a close-up image of the Perseverance, and this is the main body of the Perseverance. This is a robotic arm. I believe this is an instrument which is equipped there at the end effector, and then there are these various scientific payloads which are labeled here, and you can see the wheels. In spite of the failure of using those curiosity wheels, NASA did not actually deploy the nitinol wheels because of certain aspects which I will address after I cover this topic. So, and historically, Perseverance is one of the heaviest rovers ever sent by JPL and NASA, which is more heavier than Curiosity. You can say by a magnitude of 100 kg. But still, they did not use nitinol wheels. So, what did they do if they did not use those shape memory wheels? They used wheels of improved dimensions, new dimensions. See, on your right, you can see the Curiosity wheels, and on your left, you can see the Perseverance wheels. You can see a lot of differences, like the diameter has been increased, the thread pattern has been changed. So this type of a thread pattern, after a rigorous analysis and study, they determined that this type of patterns have more load bearing capacity, and the thickness is remaining same, but they have a very sturdier inner frame for preventing any sort of failure, and they have used thicker aluminum wheels in this case, and that makes a lot of difference in performance of the rovers. So the dimensions are mentioned numerically, and you can see that, and that change was there. So why did they not use nitinol instead of just uh, improvising the already existing design? It is because these nitinol shaped wheels were in development stage, and they are not yet out for this type of space missions, because there are other aspects as well to consider. We were sending something to space, because you cannot just afford to take so much of paramount risk, because as they involve a lot of money, resources, energy, and effort. So it is still in R&D phase, you can say research and development phase. So when they come out, then it will be definitely a milestone achieved by all of these engineers in NASA. Now let me finally address this last topic, which is how you can perhaps build your own rover. So as I already mentioned, like before you even think of building a rover, you need to understand the surface which you will try to explore. So which means you need to be aware of the kind of surface you will subject your rover to, which makes you to put a lot of thought into what type of terrain you will explore. Say for example Mars. So then you need to make systems which will be able to do surface exploration. Now somebody in the webinar asked me a good question, that why do not we deploy drones instead of these wheeled mechanisms? Because you see the drones are flying, so they are not in contact with the ground, so all of the traction issue is solved apparently. But actually drones are flying, and they maintain a lot of distance from the surface. So drones will be used for image capturing and all, but you will never be able to conduct any sort of on ground experiments. You cannot drill and do soil sample collection and put it on board, because maintain the aerostability will be challenged to much more extent, and also you will never be able to uh, efficiently investigate the surface of the planet you are trying to explore. So drone and all those hopping aerial mechanisms are put into action for very low gravity environments like the moon. But for planets with very high gravity environments, you need some sort of system which is very stable and sustainable for very long operations as well. Because, and another aspect I would like to address here is that you see these drones will be subjected to these winds, various storms. Like in Jupiter there is this red storm, in Mars there are various Martian storms, there are lunar storms which are extremely deadly, and they can just kick off the drone in one single strike. So maintaining aerostability, all that while understanding the various wind density patterns around your drone will make it extremely challenging to maneuver the drone forward. or even stay stable for that matter. So your pictures will be extremely hazy and things will not be stable at all. So if you deploy this type of a wheeled mechanism, no matter how harsh weather condition comes, in most of the scenarios it will, kind of stick to the ground inertia and try to maintain traction, and it will perform better experiments and have more stability overall. So I hope that answers your question, right?
Yes, yes.
Okay, thank you. So here you see that these how you can actually go about building. So you need to consider the various subsystems which I've already mentioned. So you need to have some guys working in your electronics and computing domain, somebody who will build up the autonomous navigation module for you. You need to select a single board computer. Like for starters, you can use Raspberry Pi, or you can use Arduino, or for that matter, you can level up and use, NVIDIA Jetson Nano, which is a single board computer for taking all decisions and all of these huge data processing tasks. So you basically need a computer which will do in a real-time data analysis, and then you will need someone to build all those control algorithms for you. You have to develop those control algorithms to control all this intricate electronics which is controlling the actuators and the sensors on board the rover. Then you need to select what type of motors will be suitable for maintaining the traction, for the rover to conquer whatever surfaces you have. For that you need to perform design analysis as well. Like you have to create a virtual environment where you will send your rover, and this can be achieved by a method, I remember correctly, it is reinforcement learning. So it is a branch of artificial intelligence, very interesting, where you create a game environment, and then you have a sort of reward and punishment policy, and using some deep learning methods, you basically train the rover like a baby child to learn moving on the surface. It will hit obstacles, it will be punished, it will try to avoid obstacles, it will build a whole new optimized path to move and rove the surface, so as to say. Then you will also need the materials to be selected very precisely, and you might think that all this might involve a lot of cost, but no, it won't actually. If you are able to do a bit of research, then you will be easily able to build a rover, and there are certain open source rover building platforms like Leo Rovers where you can do that, or even JPL for that matter has a website where they are selling this type of rover making kits. But without using ready-made kits also you can make by conducting some real original research, and that should fuel up your interest in space science as well. So then you need to design these tires, and 3D printers will help you a lot in this aspect, because when you are able to 3D print your designs, you are basically doing some actual stuff instead of just putting or plugging in some sort of ready-made objects. And then you have a motor controller to control all these motors. You need a
And
Arduino to control all the sensors, and you also need some sort of communication systems to have this autonomous navigation module enabled here. You will need to build a robotic arm as well, which will have say 6 degrees of freedom, say, for achieving tasks like picking up a sample. There should be some cameras, like you can install a gimbal camera which can do the image processing for you or take images, and that way it will be able to navigate the surface. And you also need a very robust design analysis, because the most important aspect of building any rover for that matter is the design. It is where everything starts. So I would like to conclude this session, and hereby I open my window for questions. Please feel free to reach out to me via the following channels, and I hope I could add value to this session.